Hello, and welcome everyone to EDIE's latest webinar, this time on improving ROI of energy projects through AI, automation, and other kind of newer technologies. I'm Joshua Neal. I'm the intelligence editor here at EDIE, and today I'll be chairing the session that will look at the utility of real-time appliance data, automotive tools for streamlining carbon reduction strategies, and how AI optimizations can be implemented without the difficult processes of replacing all your current systems. We've got about 45 minutes today to explore the topic. There will, as always, be about half an hour of presentations followed by 50 minutes of audience Q&A. As we like to get through as many audience questions as possible, if you think up something during the presentation or have something you already want to ask, it's always good to put it in the Q&A function at the bottom of the chat here as soon as possible, just so we have some questions lined up and we can kind of get into it as soon as possible. There's also the upvote function, which you can upvote questions that have already been asked if you want to hear them, and that way we can prioritize what gets answered first. This event is also being recorded and will be sent to you after the webinar is done via email and available on our site as well. Before I introduce our speaker today, I'll just set out some context. I am sure everyone watching is aware that there's increasing pressure on sustainability teams to demonstrate ROI of their sustainability and energy projects. As budgets are continuing to get tighter, the need to demonstrate success or measurable returns is mounting. The traditional ways of doing this are failing to keep pace with business demands, though. As organizations increasingly pivot toward any projects that can show demonstrable and often short-term ROI, sustainability teams need to find new ways to create buy-in for energy projects that are often longer-term and challenging to quantify than some others. And that's where newer tools such as AI and automation can assist. These can drive value, cut costs, and create efficiencies almost immediately upon integration. To talk about this today, our speaker is Adam Wright, Product Director at Measurable.energy. And Adam, if you would like to come on screen and begin your presentation, please.
Perfect. Thank you very much. Okay. Right, today, a masterclass in how AI and automation can fast track your energy ROI. So we've got a lot to get through, so I'm just going to dive straight into this. Okay, so let's start with looking at what's happening out there. You know, what's actually happening out there in the real world of sustainability and energy reduction. And I think the first key point here is that, you know, cost reduction is sustainability. You know, there is no separation between a solution that reduces costs and then has positive sustainability outcomes, and that's reflected, you know, now in the challenges that say sustainability teams face. You know, the pressure that's on them to deliver fast, to get you know, positive sustainability outcomes, but also cost reduction in that, so that they are one and the same. Traditional energy management is not up to the task of what we now need to do. It is holding teams back, and I want to talk about a few of them. So, you know, legacy BMS systems. I saw a fantastic stat the other day that showed that 80%, if not higher, of BMS systems are actually over 20 years old, meaning that technology in many buildings isn't able to cope with the modern requirements of hybrid working and you know, various different levels of occupancy, but also integrate with other systems. Static baselining, so, you know, taking 1 month and just comparing it to another one and expecting to see some good accurate results by comparing those. You know, the use case of what goes on in a building is it can be drastically different month to month, and we're expecting that to be able to show us where our reduction's coming from. And then manual analysis in terms of getting data out of things and then needing people to go through it, you know, where we haven't, you know, we have many tools available to us now that don't need, you know, to use those. Now, it's a bit of a minefield out there. There are quick wins through AI-driven energy control. You know, that's kind of, you know, a given. You know, we've seen We've seen the rise of AI across almost every aspect of our lives, and managing energy is one of like the kind of key areas. But the whole landscape is quite littered with buzzwords, and there are different levels of success against AI energy tools. I've seen stuff like an energy management platform that has a GPT integrated into it, and now it's branded as an AI energy management tool. That's not necessarily the kind of AI that we want within energy control. And then makes it more difficult to find the tools that are the right ones to go forward with. And the other key thing I think that's coming out is that there is value beyond energy through smart integration. We have legacy systems, we have legacy tools, some things which can still provide value to us when they're enhanced with some of our newer technology. And integration is such an important piece. And I'm not talking about integration that requires weeks and weeks of engineering time to do. I'm talking about the kind of integration that you can do on day one of installing a system. So with that in mind, we're going to go into sort of how this would work out in sort of real life. What can we actually look at? Where can we actually make a difference in buildings? And I think the starting point here is that we live in this world of wasted energy. At Measurable Energy, we've been able to generate a lot of data on what's going on in buildings, and from that we can see that around about 40% of the energy use in a building is coming from plug sockets and appliances that are plugged into those plug sockets. And about half of that energy is just wasted. Things left on, hot water taps boiling overnight when no one's there, electric heaters left on, TVs, monitors, computers, printers, all things plugged in using energy when people aren't in the building. And there really isn't a good way without manual intervention of being able to go and address that. But also within that, that energy use that's happening out of hours, these appliances that are getting used when no one's in the building is also directly linked into other systems that are in that building. So what if there's no one in a building? Why have we got HVAC still on? Why do we have lights still on in certain areas? And though traditional tools exist to be able to go and address these, they're very, very manual and set up, and there's less dynamicness in terms of these changing schedules. So what I'm going to do is I'm going to kind of take you through a bit of a real world example of how this can work. So let's start in an office building, and we've got a computer with say a monitor. It could be a laptop computer, it could be a desktop, and someone's working away. They're using active power on there, and it's very clear that there's energy use going on there. And they get up from their desk, and that desktop goes into standby, or they take the laptop away with them, and the monitor goes into standby, and off they go. And we have this sort of wasted energy that's left there. It might be small, it might just be a monitor, it could be a bit larger on a desktop computer, but we've got energy use there. So what Measurable Energy does here is uses those plug sockets to then turn that appliance off. Okay, so we know that one desk is not in use anymore, so the system can go and turn that off. Great, we've made an energy saving. But when we look in the wider office, there might be the whole office or a whole area of an office that hasn't now got anyone using those computers, and we've got a whole load of standby energy there, monitors or desktops that are in standby, not being used, and so we want to go after that as well. So we want to see that pattern, and we see that kind of that almost that sort of insight into sort of the use of the building from that. So let's go ahead and turn off all of those appliances that are wasting energy. Now we know that office area, or that floor, or even it could be the whole building, doesn't have anyone in there using energy on those desks. But if we flick over to the meeting room, we see that there's a whole load of standby energy, and in some cases active energy, of appliances left on. We've got a TV still using energy, AV equipment still there, using energy when no one's there. So let's turn that off as well. Let's get that turned off. And then we fly over to the kitchen. We see that there's still a hot water tap there in its standby mode, and its standby mode is still boiling hot water at a time when we know that no one is in that building. So let's go ahead and turn that one off as well. And you can kind of see a bit of a picture here building. There's, the appliances at the start are leading to give a picture of what's going on in the building based on energy use, on whether they are being used or not. And the context of knowing what that appliance is really driving that. So when we go to the next step out, we see that there's buildings sort of all over the place that have appliances that might be, on, and people in there, using them. But then they have their periods of time, whether or not that's overnight, at weekend, and a holiday time, a bank holiday, whenever it is, where the appliances are not showing predominant active use. And we've got this pattern, emerging of when things can be turned off. And that pattern is dynamic because, if for one particular day out of a month or a week, there was more energy use or more active use, or people were using that space, it's reflective in the energy data that's coming through from there. So we've got this sort of responsive and dynamic system that's able to then, look at what is actually happening, in that building, and then make decisions about saving energy or optimizing that, that space, off that. And this is happening in all sorts of different buildings. We've used commercial offices there as an example to show sort of how that appliance identification, works, how it gives the context to how you can and can't turn things off. But it's applicable to, offices, retail, hospitality, hotels, estates of schools, anywhere where there's this pattern of use that can be derived from it. And it starts right down at the bottom at that appliance level, and then from there can move to other systems as well. So what we're talking about here is energy control without the complexity. Okay, the beauty of this kind of AI, or using AI in this way, is that it works independently when there is no BMS, but it also then provides a BMS with extra value and extra points to start turning things off at different times. So if a building does not have a BMS, it is a costly upgrade to go in and look at that. And not every building could warrant that the kind of spend of putting in a full BMS system in it. Some will, and there'll be obvious reasons why you would do that for a good payback. But there are scenarios where maybe a building is smaller and there are lots of them, where it doesn't necessarily make as much sense to go and put in a full-blown BMS system. But what the measurable system does with at the plug socket level and automatically is essentially provide a mini plug load BMS that is then able to drive further savings. So for example, it's picked up the pattern of when people are there and they're not. It's turning off the appliances that are wasting energy when no one's in the building, but it's also then able to tell a lighting system or another system that's in there that the pattern exists here, and that there are more energy savings to be had by following that. When the building does have a BMS, then it's there ready to get plugged into that. BMS optimizations can often, especially on older ones, can be often be quite costly. If we've got this extra level of intelligence that's providing, real time sort of space utilization in that building based on that real raw parameter, which is of occupancy, which is essentially the energy use in the building, that can then plug in to generate more savings on HVAC, lighting systems, as well as inform as to is the space being used correctly. What it means is it's an incredibly low capex and fast payback way. It is not investment heavy, hardware heavy in terms of in terms of the cost going in to do this, and it means that ROIs can be achieved quite quickly, and it lines up really nicely with that cost reduction being a part of sustainability. Getting a system like this installed, is done in minutes rather than months. Changing, a plug socket, plugging in extension leads, is a quick thing to do. A whole system can be up and running, but by the end of a day, rather than maybe weeks of commissioning, baselining, that kind of stuff. None of that's needed with a system like this. It makes it quick. To be able to achieve that. And then the kind of, the offshoot of this is that, the AI in this is essentially what it's doing is it's allowing space optimization without tracking a person. So it doesn't know, who those people are, that are in there, but it has an idea of the number of people that might be in that given building based on the desks that are there, working, the appliances that are being used. And it is a pure signal of, space and desk utilization that can then be used to, drive further data, improve other systems, on top of its ability to just save energy. So let's go into and have a look at some, case studies, some businesses that have deployed it and are using it, and some of their results. So I'm going to talk about Dalkia. So this is an office environment. It's got a mixture of desks in a sort of an open plan, a desk environment, meeting rooms, kitchens. The appliances that are plugged in include things like monitors, laptops, TVs, AV equipment, printers. There's hot water taps in the kitchen and other kitchen appliances. And one of the kind of key bits here was that, this is, a business that puts a lot of emphasis on, on security. And one of the requirements that they had here as well was that whatever system that they deployed had enterprise grade security. And that's kind of, part of the measurable energy offering. So, within that and within the install, it was very quick to get to a point where the energy was reduced by 52%. This is turning a mixture of appliances that were left on standby, but also appliances that didn't have standby mode or weren't programmed into a standby mode and were just left on continuously. And with that, there was a 49% reduction in carbon emissions. So it's essentially that kind of that combination of the cost reduction and the sustainability outcome are absolutely linked in here. And on one and the kind of key or sort of one of the key things for them was that they didn't want something that they would be having to manage. They didn't want something they're having to log into constantly or manually setting things up. So this became something that got installed and is now working, in the background. Some of the employees are aware that their sockets are a little bit different to the normal ones, but for the vast majority of people, they just continue with their day job, and these savings are realised when they're not in that building. Okay, so another case study is a company called Hospitality Energy Savings. So they were working with the University of Reading in this example. Now the sockets were deployed in a whole building that had a bar, restaurant, kitchens, kind of a co-working space for students. There was a significant reduction in plug load energy waste and similar kind of percentages that are out here. But what I'd like to focus on or sort of kind of highlight in this one was that very, very quickly there was an anomaly within energy consumption detected in their bottle fridges. So there were 5 bottle fridges in the bar area, and each one of them, when they were plugged into the measurable energy socket, was shown to be using nearly 10 times the amount of energy that was listed on the spec sheet for those fridges. The university made a decision that they wanted to replace those, so they bought 5 new energy efficient fridges, recycled the old ones, and the immediate results were an 89% reduction in energy use. And across those 5 fridges, it accounted for £12,000 worth of yearly energy savings from moving to those new fridges. They obviously paid for the fridges. They also paid for the whole installation in that building. They achieved full payback in well under a year, and that was before they even started turning stuff on and off. So now they're just banking those energy savings on top of those initial things that they found on there. And this is one of the kind of important parts of, you never see that at the meter. You might be able to get an idea that there was a high amount of energy use coming from a particular meter point or a circuit point, but it would take a very large amount of manual effort to go and find that. And this is the kind of thing that AI is designed for, is bubbling up these things that are difficult to manually find and bring them up to the surface so that they can be actioned and a positive outcome can be achieved from them in terms of a cost reduction, and some sustainability value too. I also want to tell you about sort of a space optimization piece that was done with the system as well, and hopefully the kind of the story behind it might resonate with some people. But post COVID in this office, the space just sort of started creeping up. So over time, the business was adding more desks as more people were hired, as it was growing, and there wasn't a huge amount of thought to it or data driving any of that decision. It was more of a once or twice a week we've got all of our desks are full, so we need more space, and that kept happening multiple times to the point where in this particular area there were 18 desks. Now the reality, from the data and the kind of looking at the actual energy use of the desks, and when people were actively using it and laptops were there plugged in and the monitors were on, and or against when it was all in standby and it was quite clear that there was nothing, no one there at that desk, showed a different picture. And it showed that there were the actual highest number was around 8, and there were very, very, very rare occasions where there was a need for more people, but there were meeting rooms available that could sort of handle those kind of overflows on those very specific days. So what this did is it took a yearly office cost of around about £62,000 for the 18 desk office, down to 14.5 approximately for an 8 desk office. The saving then equates straight up to £47,000 that's saved straight away, and that's pure, office, no longer needing to spend that money on, on that office space, and then of course on top of that you layer on, the turning stuff on and off, saving energy, finding anomalies, all of these kind of extra things into it, and this also speaks volumes to the fact that we're just talking about the direct cost reduction in space here. But there was also other things that were happening here. There's a HVAC system there and a lighting system that is overspec'd for a larger office space than it's need to. So there are other savings that come into this. But this is one that our system can directly show. And in this case, it meant that the system paid back in 11 days and delivered its value from there. Okay, so we've got through quite a lot of of information here, so I kind of want to pull it back into sort of like a summary that pulls this together. So what the real point I want to get across is that when you have real-time appliance data, it just leads to being able to find quick wins. Whether or not those quick wins are straight up energy reduction when in times when a building's not in use, or whether or not they are space optimization and desk utilization, and why have we got more space than we need, or the other way, do we actually do need more space, and we've got the justification to say that we should spend more on space here. And then on, by knowing what those appliances are, knowing that the energy pattern, being able to get those savings, it trickles then up to other systems. It then informs in a much more granular way decisions or automations that can be made into BMS systems, other systems that are in the building. Automation has evolved. It is just different now. We do have we see this in the energy management world almost every day, that the kind of automations and integrations that people are asking for in buildings are not the same that a 20-year-old BMS system was built to perform. There is this need for systems to be able to talk to each other, not necessarily with bi-directional or lots of communication back and forth, but being able to take prompts from set parameters that might happen in that building, like no one is in this area of this building. Bring the heat down. Turn cooling off. That kind of thing. And it's got to this point where it's just not scalable and feasible for us to have these systems where a person constantly has to manage it. We've got the tools now, to be able to not have to do that. So we should be using them. Change the socket, not the system. Some of those the quickest wins come from simplicity. There's always the case for saying that a whole building can be looked at a redesign, and there's always going to be retrofit, and we do have an aging building stock here in the UK, and there are always going to be cases where it is worth ripping out existing infrastructure and starting again. But there are many buildings where it's just not required, and it's overkill in terms of cost, time, effort, and even the rewards for doing it. Something as simple as swapping the faceplate on a socket that can then lead to so many different value propositions, is in many times is the thing that we should be doing, or we should be looking at, and a very, very quick way of getting AI into a building without a lot of investment. And the reason why why we should be even looking at any of these is because they're proving up this the ROI is fundamentally the most important thing here. And a lot of legacy systems, a lot of legacy things that we've done in the past, like static baselining and things like this, they don't always fill the building owners with confidence that they're achieving some of those those reductions. We see on paper savings or hypothetical savings that then don't line up with the reality of the actual energy bill, and what has been what's actually been spent in that building. But when we bring AI into it, it allows us to use these tools that are checking against but if that it's these appliances use this amount of energy in standby, and that appliance is in standby at the time that you turn it off, and its historic pattern was that it always stayed in standby, then you can very accurately project across what that energy saving would have been. If you know that printer has a multiple different standby modes, and it goes down in energy use over time, you can project those those into the savings over time. And what it means is we get this end result where we've got, reported energy savings that can be lined up against a bill and give people confidence to sort of move forward with these sustainability projects and energy management projects, and actually get the savings that are kind of described at the time that they were proposed it. And that confidence comes from really measuring those outcomes, and not basing it, on sort of early assumptions that we had. So I can see there are some questions there. So, well, thank you very much for listening. And I can start taking some questions.
Yeah, brilliant. Well, thank you very much, Adam, for your presentation. And yeah, we do have quite a few questions, so I'll dive right into those immediately. We have two here that I think are semi-related, which are about the sort of, I guess, the flexibility of the system, which is someone's asking, if the outlets are needed again outside of expected hours. Are there like processes for that? And another person's asking in terms of if they don't work, people disengage rather than investigate, and how do you ensure uptime and occupants don't end up locked out of whatever they need to use? So in terms of the out of hours times, do you want to talk through that?
Yeah, no, both are really good questions, and yeah, you're right, very very linked. Yeah, so look, the hardware is designed to be, to the untrained eye, be as close to a normal socket as possible in terms of the behavior of how it would work. So we have buttons on the on the sockets themselves. So every single socket is overridable. So if someone arrives in a building, say the building always gets turned off at around about between 8 and 9 p.m. or something like that, and then suddenly there's something going on and someone's come back at like 11 o'clock at night and it's completely out of the pattern, those sockets will, whichever one they want to use, will be overridable by the physical button that's on there. So if they've got no access to the cloud reporting system, or access to log into our system, they'll always be able to press the physical button on the socket and get access to it. If the button's not accessible because it's behind something, then in many cases we use things like a QR code that someone can scan and get access to the to that socket. They could also, if they've got access to log in remotely, log in. There was also a feature that we have specifically for things that people want to monitor but they never want to turn off. And the key one that always stands out to me is that quite regularly we go on to things like server racks in an IT server room. Yeah, it's so critical to keeping that running and keeping it going for the business, but you're never going to turn that off. So we have a super socket mode, and those sockets are designated as within the platform as a socket that is not eligible for rule set. So it will not be included in the AI that works out what it can and can't turn off. So those would stay on. Other examples we've seen, hospitality as well, where there might be one or two key appliances that they want to know what the energy is costing them, what it's using, but they want to keep that on because it's a very critical appliance for that for that particular business.
Brilliant. Okay, well, thank you very much. We have another one as well that's been uploaded a few times, which is also about the sort of technicalities of things. But someone's asking, is there a visible dashboard that can show anomalies and savings for the customer, and can you integrate alerts and notifications for when an anomaly is flagged?
Yep, really good question. Yes, yep. So the system, the system is driven from a cloud-based platform that has all of the data that's coming from those those plug sockets, goes up to up into that cloud. We perform a little bit of machine learning on the edge itself, which allows us to do some of the identification, not send huge amounts of data, and then the pattern recognition happens where we've got the data from all of the different sockets. End users can log into that platform. They can view live energy data of what's going on there. They can see energy patterns. They can set up things like web hooks to get alerted at certain things happening, see anomalies, set up reporting to get reported on you might want to get reports or get notified every time a a socket trips, for example. Too much energy is going through it. There is a safety mechanism in them. Or you might want to get notified that things have gone offline, or something else is going on in the building. So all of that is available in the platform.
Fantastic. We have another two linked questions, I would say, in terms of the location of things. So we have one which is about does it work for lease buildings? Um, and the other about more complex systems like factories, and could the system be applied there? So if you want to talk
Yeah.
about, yeah, different areas it can be used in.
Yeah, sure. Yeah, no. Yeah, so a large number of the places where we're installed, they are lease buildings. So the sockets themselves are literally just a faceplate. So the wall sockets are a faceplate. The fuse spur is just a faceplate. We've got extension lead versions as well, so they just plug into any existing plug socket that's there. We've had business in the past that have been leasing a building. They've had their sockets installed, and then they've taken them with them to their next building afterwards. Yeah, we've not come across any issues with changing plug sockets within the leases.
Cool. And in terms, oh, sorry, go on.
Oh, and manufacturing, yeah, and sort of industrial, yeah, yeah. No, so we've got installs that are in sort of like manufacturing environments. We're not necessarily the plug sockets obviously are not measuring the energy of some of those big three-phase like machines that you've got in there, but within those manufacturing environments, there are still often office areas, kitchen areas, lots of places where there is plug energy that we can go after. We can tap in sort of three-phase monitoring and take in energy from from sort of bigger appliances or machines. We're not turning those off just because they all have custom shutdown schedules, and it's the last thing you'd want to do is turn off a big like a CNC machine and it doesn't come back on. But we can identify the same energy patterns and the same use patterns. This machine was in standby for 1 week, and that cost £150 to keep it there, and that's happening 1 week out of every month and costing this amount per year, and it's happening on 50 machines. So that kind of, so we can provide the sort of the analysis automatically, but we don't necessarily go with the three-phase stuff, go to turn it off.
Cool. Okay, this is one that I don't understand what this means, but hopefully you will. You mentioned
Yeah.
connecting to the BMS. Are these devices LoRaWAN compliant, or do they have their own connection protocol?
Yeah. Okay. So all of our hardware uses Wi-Fi. So it uses 2.4 gigahertz Wi-Fi. Yeah, we've got a whole load of security certification that's allowed us to get deployed into things like banks, military manufacturing, the NHS, places like that. It then that from there, the BMS integration can happen in multiple different ways. So an older, maybe on-site BMS, are kind of our patterns that we're recognizing can basically be sort of almost extracted, and those same patterns be programmed into an older BMS. And with newer, more cloud-based BMSs, we have a whole API and webhook system that can be set up to then integrate, and that integrates into BMSs like Trend and things like that.
Cool. Fantastic. Okay, we have one that a few people are asking about, and obviously is I think quite sort of topical right now, which is in terms of the carbon footprint of the AI tool that's
Yeah.
used. And do you know more about that and kind of what the net carbon saving is after that's been reduced, etc.?
Yes. Yeah. So yeah, we publish all of this on our website, and so every product that we've got, including the cloud side of it, we have LCAs done for them. So we also have an EPD that goes so that we can qualify the system to work in for BREEAM ratings, for example, in buildings, and that's calculated our kind of like carbon cost of hardware, the system working, the software side of it, and that gets factored into kind of the energy savings and the reductions that were there. If anyone wants to see the LCA APD, it is linked on our website, and we can share that.
Cool. We've got another one about the sort of the process itself, which is someone asking about whether there are sensors. So does the power to the PC is it turned off automatically after X amount of time, or does it know that it's specifically not being used and turn itself off?
Yeah, sure. So this is a really good question. So no sensors. And this is part of the whole kind of like value prop. We're not needing to add loads more hardware, loads more sensors to be able to kind of do this kind of smart stuff. That quite simply, it's looking at sort of the active energy and standby energy. A traditional smart socket that you maybe get from Amazon or something like that is not going to give you that kind of like the granularity of data. It tells you what power is coming through that socket. Ours are monitoring about 12 different parameters of power. And those 12 different parameters of power allow us to see a very, very different picture in terms of what's happening when an appliance is actually in use. So when a computer is plugged in and charging and someone's using it, or a monitor is actually got the screen on, same with a TV, things like that. And when it's in standby. And when we've got that clear sort of picture between the two, it basically allows us then particularly when you've got multiple things. So for example, you've got a computer plugged in and a monitor on the same like extension lead or the same plug socket. And if both of those are not showing active power, the charger has got nothing plugged into it and the monitor is in standby, you've then got your very kind of clear picture of that's not in use. Now, it's not generally a case of the second that something's not in use, turn it off, because it is more about sort of like the wider pattern, in that area. So, you could have, you could still have 4 or 5 people, still working in there, but you wouldn't necessarily go and start turning everything off straight away. You can, but the kind of the premise is to be a little bit more conservative and allow it to get to a point where there is no active energy in that area before then saying, right, now we can turn stuff off. Because the last thing that we want the system to do is disrupt anyone to the point where it's like something that has to be raised. And that's our focus is being a kind of under the radar, sort of almost energy saving, technology that the vast majority of people don't even realize is there.
Cool. As a follow-up to that, there's a new question about, could you elaborate a little further on those 12 different parameters of power that you referred to?
Yeah, sure. So we're talking about things like active energy, reactive energy, power factor, frequency, um, you know, and a few others on top of each other. But those are probably the main ones that give us our kind of identification. And what happens is the first point that we use that is that the second that someone plugs something in, when we see essentially a sort of like a spike of energy to get going, and across those parameters, it allows us to give us the different picture of what the different appliances are from that.
Sure. Okay. And this one's a more broad question about something you were referring to a little while ago at the start of the thing. But given the energy intensity of heating water,
Yeah.
could you give a general rule of thumb regarding turning off that kitchen hot water heater in terms of, is it only worth switching it off after if it isn't going to be used for a certain amount of hours and that sort of thing?
Yeah, so it's a good one. So a lot of what we've been finding is, or kind of when we really started here, is that there was a lot of kind of looking at, when is the value for actually turning stuff off, and for fridges, actually bottle fridges in hospitality, we do quite a lot of those as well. They fall under this kind of remit with heating water. So there's an argument to say that our preference is to turn off like water heating things for generally like overnight, and maybe a slightly more extended period on a weekend, and not much more than that. And that is because there is exactly that sort of value trade-off. If you turn something off like that, like a water heater, for too long, you've obviously then got the heating up of it back again. But if it's not going to be used for 2 weeks, it's very worthwhile to turn that off for 2 weeks and then just have the energy, to then boil it back up. No point. So there is a little bit of a balance here, with those appliances, and there is, no good AI or machine learning works without a small amount of human in the loop. And our human in the loop is very much at the beginning when we're getting a site set up. So what are the caveats, or what are the extra information that we want to feed the system, so that it doesn't do things that are unwise for for energy savings. The bottle fridge one as well is like because I'm going to mention it, I'm going to go into it. So what we saw, and it seems probably very obvious, is that if you turn a bottle fridge off and then someone opens it, you've lost all of your energy saving, because now the cool air has escaped, and when it comes back on, it's going to have to work hard to get that back to temperature. But if you turn it off for 6, 7, 8 hours overnight and no one opens it, so it's definitely off at a time when no one's in that building, then by the time it comes back on in the morning, the energy spike is almost non-existent. It's not even noticeable, and you're just banking energy saving. Obviously, we've got to take into account if they were going to turn that off for a week, there will be probably an energy spike to come back. So it's that balance of what makes sense from an energy point of view, and and what and what you can and can't turn off.
Brilliant. Okay, well, we're about at time now, so I'll ask one more question. I've saved the hardest and for last. Do the sockets come in different finishes, e.g. stainless steel?
Yes, yeah, they do. So our standard is just a white, socket for them, but we can essentially do almost any color that's wanted there. We don't have a metal finish, but we can do our plastics in different colors.
Brilliant. Perfect. Well, thank you once again, Adam, for coming today and giving your presentation, answering all our questions. Thanks generally to Measurable Energy for sponsoring this webinar and for kind of bringing this topic to us. And thank you, the audience, for your questions and for participating and listening in. I have one more thing to say, just in terms of wrapping up, which is that ED26 has the final members tickets now gone live. ED26, our flagship event, is on the 25th and 26th of March in London. You go online or to our website or scan that code. You can get the member rate now. But that is all for today. Otherwise, thank you once again, Adam and Measurable Energy. And we'll see you all again next time. Thank you very much. Cheers.
Right, thank you.